Well, welcome, Earth Space class. Attempt again at a video lecture. In putting this one together, it was particularly difficult to do this without being able to do demonstrations with you in a classroom. I'm going to do the best I can with the images I've got, animations that I've got, but just know that when we get back in the classroom next week, I will have some demonstrations for you, things that I think you'll be able to adapt to an elementary classroom to help kids understand some of these complicated concepts. And really, I think I think we'll have some good demos for you. So anyway, we left off talking about the sun. Hopefully you went back on Moodle and reviewed the clip on the sun that I had recorded and embedded in the last lecture without a proper sound. The recording application that I'm using doesn't, or I haven't figured out how to let me switch microphones to a computer and back and forth in the middle of a recording. So I'll probably continue to do that today as well. I have a clip that I want you to view in the middle of this lecture, and so I'll have you pause the lecture and go view it. It's not a big deal, but just a little clip, maybe two. So anyway, we left off talking about the sun. I wanted to mention a couple of items. Measurements of distances. We've already talked about astronomical units. And there's a couple of more distance measurement devices that we use in astronomy. One of them is the light year. No, it's not a low-calorie year. A light year is the distance light travels in a year. So if you were to take a flashlight and turn it on, okay, I had to run and get a flashlight there for demonstration purposes. So if I was to turn this flashlight on and kind of measure, or do it from this end, the distance that light traveled in a year. So if I turn it on, let's see if I want to blind everybody. Okay, how long does that light, how far can that light travel in a year after I've turned it on? Now, of course, that light, the beam of light that comes from this flashlight is going to get diffused to virtually nothing fairly quickly. You know, probably a mile away, you wouldn't even see this light because it's not intense enough. But some lights, you know, good lights, lasers and such are able to be generated with enough intensity that they can go a long distance and still be visible. They will diffuse or scatter as they move away from the source. But if they're intense enough initially, you can continue to view them. So with that in mind, thinking about this flashlight and how far light generated from it would travel in a year, you know, how fast is it moving is the next question. Well, speed of light in a vacuum, which most of space is 186,000 miles per second. That's pretty quick, okay? So when I turn this light on, in 1 second, it has traveled 186,000 miles in a vacuum, which it's not here, but it's close. It's going to travel a long ways. You can't see light traveling. I mean, it's too fast. Your eye can't follow it. So if you do the math, so if light travels 186,000 miles in a second, in 1 year, that would mean that light, that beam of light, would cover 5,900,000,000,000 miles. That's a light year. That's the distance light travels in a year. So we will talk a lot about light years. In fact, you will see it abbreviated just LY. So just think about that. The speed, you know, the distance light would travel as fast as it's moving. If it were to move that for a whole year, how much area, how much ground, how much space would it cover? It would cover 5,900,000,000,000 miles. Another one is parsec. And I'm going to include a link here to an old Star Wars clip. Well, if it'll come up. Uh-oh. They're not behaving. Let's see here. And it's the old Star Wars. Uh-oh. The old Star Wars scene where they are, yeah, there we go. Where Obi-Wan Kenobi and Luke are in a bar, and they've just met Han Solo, and he talks about making the Kessel Run in 12 parsecs. Okay, so I'll include that link on there. Well, what is a parsec? Well, the way it's framed in this particular video clip, it sounds like it's a unit of time, a measurement of time. In actuality, a parsec is not a measurement of time. It's a measurement of distance. Now, this is not in your notes. I don't think it's in your notes, but I'm going to include it in your notes. So maybe I'll even edit them a little bit later and reload them into Moodle. A parsec, you'll see it often enough. It's worth knowing what it is. It's another unit of measurement in astronomy. So here's the I won't expect you to know this, but if you look at a parsec, so here's Earth as it's traveling around the sun. There's that distance that the Earth is from the sun, 1 astronomical unit, about 93 million miles. Okay, and here's a star that's a near star. So if you were to draw a line from Earth to the star and from the sun to the star, and then extend that beyond, and if that angle that you get between those two lines is 1 arc second, so there's in every degree there are 60 minutes of angle, and in every minute of angle there are 60 seconds of angle. If that is 1 arc second of angle, then that star would be said to be 1 parsec away. What I want you to remember, that's the explanation. I'm not going to test you on that. What I want you to remember is that 1 parsec is equal at about 3.26 light years. 3.26, so about 3¼ light years is what a parsec represents. Okay, so light year and parsec are 2 more units of measurement you will see commonly used in astronomy. Okay, so let's get to the Earth. Earth, just shy of 8,000 miles in diameter, and it's spinning on its axis towards the east. Okay, if you think about the sun rising, let's see if this will behave here. There we go. If you think about the sun rising, the sun rising, it looks like the sun is rising in the east and setting in the west. Okay, so it looks like the sun is moving across the sky from east to west. To make that motion, because the sun is it's not totally stationary, but it exists in the middle of our solar system. Okay, to make that apparent motion, the Earth has to be moving towards the east, like you see here. Okay, so because the sun, if you picture the sun being stationary over here, and if we're moving as the animation is representing, then here we go. Then advertisement time. Then it's going to make the sun look like it's moving across the sky east to west. The problem with that is you can definitely find problematic representations of the Earth's motion. Here's one. I found it. Didn't take too long to find it. Storybooks. Story blocks, too. I don't know, something for elementary kids. Unfortunately, folks, that Earth is spinning the wrong direction. Yeah, so be careful what's out there. This is not how it is moving. Let's see if I can go back to this one. There we go. If it will do it. This is how the Earth is actually moving. Okay, and you can see the United States kind of disappearing, if you will, into the daylight. Yeah, and so that makes this motion of the Earth makes the sun appear to rise in the east, set in the west. It also makes the moon appear to rise in the east and set in the west. It also makes the stars, some of the stars that are not near the north celestial pole, near the North Pole, it makes those stars appear to rise in the east and set in the west. Okay, so keep that in mind. It's not just the sun, but all those planets, because the Earth is moving like this, all the planets, the moon, the sun, all appear to rise in the east and set in the west. Actually, I'm going to go back to the one. I'm going to pause it. I'm thinking that may be giving me some troubles here. So one of these sites is giving me trouble, so I'm going to nix out of some of them here in hopes that some of the others will work a little better. Maybe they won't. At any rate, while I'm fiddling with this, the Earth is tilted 23.5 degrees on its axis with respect to its motion around the sun. Boy, this is really being problematic. We'll see if it will behave here at all. I'm going to have to pause this video recording and try to fix this. I'll be right back. Sorry about that, folks. I may pause the recording again if it continues to give me troubles. It's my recording app seems to be interfering with my websites that I've got open. At any rate, so the Earth is tilted 23.5 degrees with respect to its orbit around the Sun. So that's what this diagram attempts to show, and here as well. So this is Earth's orbit around the Sun. If that were a plane, then Earth is tilted 23.5 degrees with respect to that. Now you need to know that that's kind of an average, that 23.5, 23.4 degrees. It actually varies within this range, anywhere from 22.1 to 24.5 degrees. And that variation, along with some other factors, so here's Earth's usual orbit, but periodically it can stretch out significantly farther. And also its spin changes. So if you think about the Earth spinning, that axis that it's spinning along, what is it pointing to out in space? Well, what it's pointing to out in space changes over, well, they say 19 to 24,000, others will say 26,000 years. So all those things combined mean Earth has some variability in it, and that can affect our climate. So Earth's orbit is definitely elliptical, though, as Kepler discovered. We said it takes about 584 million years, or million years. It's about 584 million miles long in its orbit around the Sun. So that's a little bit of a wander. So then I wanted to talk about why we have seasons. So if you talk to your elementary class and you ask them a simple question, why is it getting colder right now? And why does it get warmer in the summer? I'm guessing, even a lot of people you walk up to on the street, I'm guessing that they would tell you that it's because we're getting farther away from the Sun now, and we're getting closer to the Sun in June. That's why it's getting warmer. And I want to make the case that that's not the case. And I will do this with a demo in class that I hope will help explain this, but I'm just going to put some words on it right now, and we'll see what I can do with that. So the idea is, and this diagram might be good enough to represent it. Right now, we are actually getting closer to the Sun. So this would be us right now. So if you look at our orbital path, this is our orbital path right here, okay? And you'll notice we're closer to the Sun right here than we are right here. But if you look also, we're tilted away from the Sun. So here's North America right here. I'm trying to put the cursor on it. Okay. And so we're tilted away. So solar energy hits us and bounces off. Whereas in the summertime, we're tilted towards the Sun. So solar energy hits us and is more directly hitting us. And so more of it is absorbed. Okay. And so, well, okay, so if we're closer to the Sun, why aren't we getting warmer? Well, part of it is the big piece of that is that tilt difference, okay? And so we're actually, as I said, closer to the Sun in December, farther from it in June, but we're tilted away from the Sun in December and tilted toward the Sun in June. Okay, so what does that mean then for other areas of our globe? So you know that if it's winter in the northern hemisphere, it's summer in the southern hemisphere. Okay, so here this would be winter. This would be us right now, winter in the northern hemisphere. But look at the southern hemisphere; they're tilted toward the Sun and closer to the Sun. And here on the other side, okay, so if it's summer in the northern hemisphere, it's winter in the southern hemisphere. They're farther from the Sun and tilted away from it. Now, to make the case, what does this look like in real world terms? Let's go to Google Earth, and let's go to McMurdo Ice Station in Antarctica. I'm sure that's a place that's on your list of places to visit. There actually is a little settlement there, a development where people, usually scientists, researchers, go and live for a while, do their work. And of course, if you've got a scientific station, you have to have support people for that. And so if we zoom in on that particular area, if I can find it, It's a small a small establishment, to be sure. It's on this little spit of land that sticks out into an icy. I'm going to get rid of these things. Into an icy, usually frozen ocean. Okay, so if we look here, we'll zoom in, and you can see some fuel dumps, some sort of basic buildings. And if we look at some of them, we'll just kind of go down to a street at the McMurdo Ice Station, the research station. It's probably what you would have expected. And if we look around a little bit, yeah, very Spartan existence, basic buildings, no doubt well insulated. The equipment that's here is here to maintain transportation. There's a little airstrip here and things of that sort, but very Spartan, not very big. Okay, so let's then go to the northern hemisphere. We'll go to the capital of Greenland. You didn't know Greenland had a capital? It does have a capital. It's called Nuuk, which is what we used to put in our kids' mouths when they were little and getting fussy. Okay, so if we go to Nuuk, Greenland, I want to back out just a little bit here. And I'm trying to make the case that the northern hemisphere, now I'm not exactly comparing apples to oranges latitude-wise, but you see we're in Greenland, we're way up north, and we're a long ways up north. And if we go to Nuuk, Greenland, it's a very different place when you compare it to McMurdo Ice Station in Antarctica. There's about 20,000 people live here. And if you go to beautiful downtown Nuuk, it may surprise you what you see. I'm guessing most people didn't think there was much more than igloos on Greenland. But in actuality, you can go to Greenland and, there's some pretty nice buildings there. Now, Greenland is a protectorate of Denmark, but it's mostly self-ruling. There's street lights, pretty nice buildings, cafe, you can get yourself a hamburger, Coke, pizza. I'm guessing that's maybe a little bit of a surprise. Greenland is, Nuuk in particular, as I said, town of 20,000. It's expanding. There's a lot of mineral resources in Greenland. And yeah, so why the difference? Well, the difference is right here. If you think about it, here's South America. We'll go over here. South America in the wintertime, farther away from the sun and tilted away from it. It is a nasty, inhospitable place. That's why the South Pole would be very nasty to visit. And McMurdo is nothing like Nuuk, Greenland. If you go to the northern hemisphere during winter, well, we're a lot closer to the sun. We're tilted away from it. But the North Pole, which is why that's where Santa Claus lives, right? Because it's nicer than the South Pole. And it has to do with the position of those areas in relative to our position in space. And again, I will try to demonstrate that with a demo in class next week. Okay, I already made the case that the Earth wobbles as it spins. We call that precession. I wonder if I had another. I'm going to just look here real quick and see if I did. Yes, I did. I had another indication of what, of another diagram of precession, if it will open. There we go. Okay, and so here's this idea. It's like a top that wobbles. As it's spinning, it wobbles, and it takes like 26,000 years to complete a wobble. Okay, but what that means is that what we're looking at for a North Star, because really Earth's North Pole here is pointing right to Polaris, the North Star. And it's that star in the constellation Ursa Minor that doesn't move in the night sky. Everything else spins around it. And so it'll stay stationary in the night sky. It's a guide star, if you will. Well, we look to Polaris, again, in the constellation, the Little Dipper, Ursa Minor, and that's right here. So in our night sky, we would look up and we would see Polaris. That's right here. There's the Little Dipper. Okay, but remember, this whole path, this would be one wobble, takes around 25,000 years, 26,000 years. We have written records from the ancient Egyptians that they didn't look to Polaris as their North Star, as their guiding star, their star that did not move in the night sky. They looked, this is 3000 BC, so 5,000 years ago. That's 1/5 of that whole path around one precession wobble, if you will. That's a pretty significant piece of it that we actually have recorded measurements of. The ancient Egyptians looked to the star Thuban, which is in this constellation Draco the Dragon. That was their North Star. That's pretty incredible. Look at all of Earth's history when there wasn't a bright star real close, and now we're pretty close to Polaris and actually moving a little closer to it. In your lifetime, we will always be looking to Polaris as the North Star. So it's kind of interesting that we actually have observational data that verifies that the Earth is wobbling a bit as it is spinning. Okay, and that's what this is trying to represent. Okay, I'm going to pause it here for just a minute, if I can. Okay, thanks for your patience, folks. I just had to pause it to pull up this other site. My computer's still not behaving correctly. The last two terms here are equinox and solstice. So if we look at this image, and this is Earth's path around the sun, we can see that it is indeed elliptical. We are closer at some points and farther away at others. There are 2 times of the year, though, when the amount of sunlight matches the amount of darkness, and we would call those equinoxes. It means equal night. And there are exactly 12 hours of day and 12 hours of night. And it doesn't show it perfectly well on this, but it's kind of like when the Earth, this would be January for us in the Northern Hemisphere, and here's July in the Southern Hemisphere. So March and September, it says the 21st. It can actually be the 20th or the 21st, and it says so that's for the spring equinox. For the fall or autumnal equinox, it says the 23rd. It can be the 22nd or 23rd. It's that point in the Earth's path around the sun when we have exactly the same amount of day and night. Then there are those 2 points when we have the maximum amount of sunlight and the minimum amount of sunlight. That would be the solstices. And in June 21st would be the summer solstice. And that's when the sun rises to the highest point in the sky. We have the longest day. The sun doesn't set till well after 9 o'clock around here. And if you think about it, the sun on that day, we probably have the impression that the sun is right overhead beating down on us that day. We're far enough north of the equator that the sun is never directly overhead. The highest it gets is about 70 degrees above the horizon. It doesn't ever get up to 90 degrees around here. And in December then, pretty quickly we're approaching the 21st of December. It's less than 3 weeks away. That's when the sun only rises to the lowest point in the horizon, just teens to 20 degrees above the horizon. And it's our shortest day. We don't have much sunlight at all. Okay. Interestingly enough, if you think about a place like Alaska, they're known as the land of the midnight sun. I was there this summer, and it's 11:30, 12 o'clock at night, and it's still light out. Sun's up. It's never, again, directly overhead because they're well north of us. The sun actually would rise. It doesn't rise. It gets. It does because it doesn't set. It gets to its lowest point on the horizon, late at night, somewhere around 3 in the morning, something like that. I'm guessing if I remember right. If you're far enough north in Alaska, it never goes below the horizon, and then it will gradually creep above the horizon until midday, 3 o'clock, 4 o'clock in the afternoon, when it gets above the horizon a little bit, but it never gets very far above the horizon. And then it goes back down towards its low point. So in Alaska, it is the land of the midnight sun, but that's because the sun never gets very high. It just kind of circles the horizon, goes all around you. And then, of course, this time of year, there are large parts of Alaska when the sun doesn't rise at all. December and January, north of Fairbanks area, all you get is a few hours of dusky light and then darkness the rest of the time. All right, I'm going to stop there, folks. Again, apologies not having good demos, but they are coming next week in class. Take care.